Okay, Assalamualaikum and good morning. Basically, in this mixed lecture, I'll be explaining on the examples of acceleration analysis. We'll not be going into much detail, but I will just do the first example. Okay, there are two examples, saving machine linkage and in-stamper linkage. So at the moment, we'll be only covering this part only. Okay, next. So let's say we have, this is actually the same example in the velocity analysis. As for the saving machine linkage, so we have a drive wheel which is rotating at 200 omega 200 rpm counterclockwise, and the link here is at 15 mm, the link here is at 30 mm, and the offset is basically 8 mm, just like the figure here. So next, so then we need to find the acceleration of AC. That means what will be the acceleration in this case, right, of AC vertically. Either it will be up or down. So we don't know yet. Okay, first we need to, so this is all given. We need to find the angular velocity of omega 1 and omega 2. So if you actually check from the previous velocity analysis, this is already given in the calculation. Okay. In this case, the angular acceleration is basically 0. So it would, this crank will rotate at constant angular velocity of 20.9 radian per second counterclockwise. Okay. So next, now the acceleration of AC will be the result of AB plus AC, okay, ACB, right? So the linkage here is that the acceleration of AC here, AC, will be equivalent to acceleration of AB and ACB, acceleration of this part and the acceleration of ACB. So how are we going to move? We are yet to discover after this. Now, the first step is really to break up the component of the acceleration into normal and tangential component. So we break up all of these components of acceleration. Okay. So the total acceleration will be of the normal and tangential, normal and tangential, normal and tangential. Okay. In this case, the point C is not rotating at all. It's not rotating. So no normal and tangential components. It's only a single value. So we do not have this ACN or AT. So that means we just take this whole value here. And then we know that the crank B is rotating at the acceleration at the constant angular velocity. That means the acceleration is 0. So in that case, there is no tangential component, so it becomes 0. And we do not know yet whether CB, acceleration CB, will have tangential or not, but we put that in case there's a value there. So we can visualize the component of the acceleration meters on normal here, right? We have a normal here going from joint B inward to joint A. Then we draw the acceleration of AC. So as mentioned just now, we are not sure whether it will be down, outwards or downwards. This is the acceleration, not the direction of the motion. So it can be accelerating or decelerating. So this will be the component of normal and tangential. The normal components are confirmed, it's always into the center of the rotation. But now the tangential component are not confirmed yet, whether it will be going up or left or right in this case. Okay, the first step is to actually calculate ABN, the acceleration of B, normal acceleration of B, right? Normal acceleration, which is equals to omega square R. Okay, so in this case, omega 1 square, which here is basically 20.9 times L square times R, which in this case 15 mm. So the normal acceleration is 6577 millimeter per second square at an angle of 60 degrees. Where do you get the 60 degrees? Simply because if you look here, this is 30 degrees, so this will be 60 degrees. Okay, let's clear first. So next is to find the ACBN, the acceleration of ACBN, which in this case equals to omega 2 square RBC, omega 2 square RBC. So omega 2 is coming from here, we already calculated. Basically, if you do this kind of equation in exam, it will be step by step. First of all, you'll be the position analysis, then you do the velocity analysis, and then you'll be doing acceleration analysis. So in that case, you do not need to actually double or triple solving before you can get to this part of acceleration analysis. So in this case, it's 11 square times 30 is equal to 3630 millimeter per second at 58 degrees angle. So how do you get this angle? Okay, you have drawn the whole kinematic diagram. You should be able to measure what would be the angle here using the compass. Okay. Sorry, protractor, not compass. You can be using protractor to measure the angle here. Okay. So next, now we can start draw the acceleration vector with a proper scaling. In this case, we have a proper scaling and a proper angle. So this is 60 degrees. Then we draw the acceleration, the normal acceleration ACBN. Okay, from this part to this part, and again we draw the possible direction of a tangential acceleration component of ACB. Okay, so the thing is that you are not sure whether it will be this way or that way. So what we do is, of course, to draw the line to denote. And next is to basically draw a line of AC. So we know that AC is vertical, there's no other horizontal component. So you just draw a straight line like this. So now, having all this, we can now conclude the direction of the AC and also ACBT. Then we measure using the ruler between this and this. Then we'll be able to get the value of this. So for this one, This will be the value. Okay, so the AC is 7950 millimeter per second square, and ACBT equals to 1620 millimeter per second square. So if you are looking at this, the direction is 90 degrees outwards. Okay, and you know that through the rotation of this, the block C is basically going downwards, but there have been a deceleration vertically outwards. So that is basically the meaning of this 7950 millimeter per second square. So we have completed to find the value. Then we can find actually what is the angular acceleration of CB. So in this case, alpha 2 is equals to alpha CBT, the tangential part, divided by RBC, so it's equivalent to 54 radian per second square clockwise. Clockwise, that means it is going this way. This is the direction of the acceleration, which is opposing to the rotation. That means this is already decelerating. Okay, let's go next. So what if it does this sewing machine have angular deceleration? So in this case, the drive wheel is decelerating at 250 radian per second square instead of constant speed. So getting the value of omega 1 and omega 2 just now, and listing down the component of the acceleration. So we got now ACM plus ACT. Again, I think this is 0. So ABM plus ABT. Now ABT exists. Why? Because there's a acceleration on the driving wheel. And then of course we keep the ACT, ACBT, so ACBN and ACBT. Then we can further reduce this into, oh sorry, this is basically the deceleration of the drive wheel. Now, so from there, of course, AC is only single component, either up or down. So we basically break this up. Not break this up. Basically, it's the same component. Okay, it's just one single part. Okay. So we maintain the new component here. Previously was deleted because it's a constant angular velocity. So now we can draw this ABN and ABT. The direction is opposed to the direction of the rotation. This is the direction of the rotation. Of course, the meaning is that it's decelerating. So next, we just use the calculation again that we have received before, which is in this case, sorry, this is the new value ABT, right? So it's equals to alpha 1 RAB, or 250 times 15 equals to 3750 millimeter per second square at the angle of 30 degrees to the horizontal. ABN we have calculated before, which is equals to omega square R. ACBN equals to 3630 millimeter per second square. This have been maintained. All the value have been was retrieved from the previous example, because this is depending on the normal acceleration depend on the angular velocity. So we can basically draw the same in the same fashion. I mean, we have ACBN, then ACBT, we just add on. Then we add with the ACBT, the tangential component. Right? This is the new, this is the tangential component of this one. Right? Now we can draw AC directly above here, going vertically upwards. That means it's decelerating at a higher magnitude due to the deceleration of A here. It was not done naturally. So by measuring, we'll be able to find AC equals to 11,750 millimeter per second square, 90 degrees upwards, and ACBT is equal to 2,100 millimeter per second square. ACBT. This component is also decelerating. Sorry, in this case, this direction. But then you can also, oh sorry, then this is the deceleration of alpha 2. So here ACBT divided by RBC, so the direction is really this way. So it is 70 radian per second square counterclockwise. So that is in this direction. So this is 70 second square. You can have a slightly different approach in drawing this. So in this case, we have, so instead of ABT and then, sorry. So instead of having ACBN and then continue to ABT, we can basically ABN continue with ABT, then add on, sorry, no,